requiring at least 2 rod and pipe electrodes spaced not less than 1.8 meters or 6 feet apart provides a more robust grounding system and enhances safety in all geographical areas. Using 2 electrodes spaced apart increases the contact area with the soil, resulting in lower resistance to ground. This improves the ability of the grounding system to dissipate fault currents and protect personnel and equipment. The panel statement suggests that in areas with low soil resistivity, a single rod may be sufficient to achieve a resistance to ground of less than 25 ohms. However, soil resistivity can vary significantly over time and with depth. By requiring 2 electrodes, the impact of variations in soil resistivity can be mitigated and a consistent level of grounding performance can be ensured. Installing 2 electrodes is a straightforward and relatively inexpensive method of meeting the grounding requirements. It eliminates the need for time-consuming and potentially inaccurate resistance measurements, which are often performed incorrectly. The requirement for 2 electrodes is consistent with other codes and standards, such as the IE 80 and IEC 60079 series. This harmonization would reduce confusion and promote best practices. The negative word explanation argues that 250.56 should be deleted and replaced with the requirement for 2 rod electrodes. Therefore, requiring at least 2 rod and pipe electrode space not less than 1.8 meters or 6 feet apart for all grounding electrode systems enhances safety, simplifies compliance, and promotes consistency with other codes and standards. Section 250.52 A5 covers rod and pipe electrodes. A rod and pipe electrode shall not be less than 2.5 meters or 8 feet in length and shall consist of the following materials. Firstly, electrodes of pipe or conduit shall not be smaller than metric designator 21, which is 3/4 inch trade size, and shall be of steel or iron, either galvanized or otherwise metal coated. Secondly, electrodes of rods of steel or iron shall be at least 15.87 millimeters, or 5/8 of an inch, in diameter. Non-ferrous rods or their equivalent shall be listed and shall be at least 12.7 millimeters, or 1/2 of an inch, in diameter. Grounding electrode systems are crucial for electrical safety. They provide a low impedance path for fault currents to return to the source, which helps to trip over current protection devices such as circuit breakers and fuses. This protects people and equipment from electrical shock and fire hazards. The National Electrical Code, or NEC, provides detailed requirements for grounding electrode systems to ensure their effectiveness. One important aspect of grounding electrode systems is the grounding electrode itself. This is the physical connection to the earth, which provides the path for fault currents to flow. Common types of grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes, also known as UFRs. The NEC specifies minimum requirements for the size, material, and installation of these electrodes. For example, ground rods must be at least 8 feet long and made of specific materials such as copper or galvanized steel. The NEC also addresses the connection of the grounding electrode to the electrical system. This connection is typically made using a grounding electrode conductor, which must be sized appropriately for the size of the electrical system. The NEC provides tables to determine the correct size of the grounding electrode conductor based on the size of the service entrance conductors. Another important consideration for grounding electrode systems is the resistance to ground. Ideally, the grounding electrode system should have a low resistance to ground to facilitate the flow of fault currents. The NEC previously specified a maximum resistance to ground of 25 ohms for a single ground rod. However, this requirement has been removed in recent editions of the NEC because it was often difficult to achieve in practice and did not necessarily guarantee effective grounding. Instead, the NEC now focuses on ensuring that the grounding electrode system is properly installed and connected to the electrical system. This includes verifying that all connections are tight and that the grounding electrode conductor is properly sized. Grounding electrode systems must comply with NEC sections 250.50 through 250.70. These sections provide detailed requirements for the installation and connection of grounding electrodes and grounding electrode conductors. Section 250.50 covers grounding electrode systems and specifies the types of grounding electrodes that are permitted by the NEC. Section 250.52 covers grounding electrodes and specifies the requirements for different types of grounding electrodes, such as ground rods, metal water pipes, and concrete encased electrodes. Section 250.53 covers installation of grounding electrodes and specifies the requirements for installing grounding electrodes, such as the depth and spacing of ground rods. Section 250.64 covers grounding electrode conductor installation and specifies the requirements for installing the grounding electrode conductor, such as the type of conductor and the method of connection. Section 250.66 covers sizing grounding electrode conductor and specifies the requirements for sizing the grounding electrode conductor based on the size of the service entrance conductors. Section 250.68 covers connection to grounding electrode and specifies the requirements for connecting the grounding electrode conductor to the grounding electrode. Section 250.70 covers methods of grounding electrode connection and specifies the acceptable methods for connecting the grounding electrode conductor to the grounding electrode. Soil resistivity is a measure of how well soil conducts electricity. It is an important factor to consider when designing and installing grounding electrode systems because it affects the resistance to ground of the grounding electrode. Soil resistivity is typically measured in ohm meters or ohm centimeters. The lower the soil resistivity, the better the soil conducts electricity. Soil resistivity can vary widely depending on factors such as soil type, moisture content, temperature, and the presence of dissolved salts. For example, clay soils typically have lower resistivity than sandy soils, and moist soils have lower resistivity than dry soils. Because soil resistivity can vary so much, it is important to measure it at the site where the grounding electrode system will be installed. This can be done using a soil resistivity meter, which measures the resistance between two or more electrodes inserted into the soil. There are several methods for measuring soil resistivity, including the Weatherford electrode method and the Schlumberger method. These methods involve inserting electrodes into the soil at specific distances and measuring the resistance between them. The measured resistance can then be used to calculate the soil resistivity. Once the soil resistivity is known, it can be used to determine the appropriate size and type of grounding electrode for the site. In general, sites with high soil resistivity will require larger or more numerous grounding electrodes to achieve a low resistance to ground. Soil treatment can also be used to lower the soil resistivity and improve the performance of the grounding electrode system. This involves adding materials to the soil that increase its conductivity, such as bentonite clay or chemical ground rods. Soil resistivity can also vary with depth, so it is important to measure it at different depths to get an accurate picture of the soil conditions. This can be done by using a multi-depth soil resistivity meter or by taking measurements at different depths using a standard soil resistivity meter. The NEC does not specify a minimum soil resistivity for grounding electrode systems. Instead, it focuses on ensuring that the grounding electrode system is properly installed and connected to the electrical system. However, it is generally recommended to aim for a soil resistivity of less than 500 ohm meters for effective grounding. If the soil resistivity is higher than this, additional measures may be needed to improve the performance of the grounding electrode system. Maintaining a low resistance to ground is crucial for the effective operation of a grounding system. A low resistance ensures that fault currents can quickly and safely return to the source, tripping over current protection devices and preventing electrical shock hazards. Several factors influence the resistance to ground, including the type and size of the grounding electrode, the soil resistivity, and the contact between the electrode and the soil. To minimize resistance to ground, it is important to select the appropriate type and size of grounding electrode for the site conditions. Ground rods should be at least 8 feet long and made of a conductive material such as copper or galvanized steel. The diameter of the ground rod also affects its resistance to ground, with larger diameter rods generally providing lower resistance. Soil resistivity is a major factor in determining the resistance to ground. Soils with high resistivity, such as sandy or rocky soils, will result in higher resistance to ground. Conversely, soils with low resistivity, such as clay or moist soils, will result in lower resistance to ground. Soil treatment can be used to lower the soil resistivity and improve the performance of the grounding system. This involves adding materials to the soil that increase its conductivity, such as bentonite clay or chemical ground rods. The contact between the grounding electrode and the soil is also important. The electrode should be in direct contact with the soil over its entire length. Any gaps or air pockets between the electrode and the soil will increase the resistance to ground. To ensure good contact, it is important to drive the ground rod deep into the soil and to backfill the hole with soil that is tightly packed around the electrode. The NEC does not specify a maximum resistance to ground for grounding electrode systems. Instead, it focuses on ensuring that the grounding electrode system is properly installed and connected to the electrical system. However, it is generally recommended to aim for a resistance to ground of 25 ohms or less. If the resistance to ground is higher than this, additional measures may be needed to improve the performance of the grounding system. Measuring the resistance to ground can be done using a ground resistance tester. This device applies a small current to the grounding electrode and measures the voltage drop to determine the resistance. The ground resistance tester should be connected to the grounding electrode and to two auxiliary electrodes that are driven into the soil at a distance from the grounding electrode. The NEC requires that the grounding electrode system be tested periodically to ensure that it is still functioning properly. The frequency of testing depends on the type of facility and the environmental conditions. In some cases, the NEC may require continuous monitoring of the grounding electrode system. Grounding electrode conductors, often referred to as GC, play a critical role in ensuring electrical safety. They connect the grounding electrode, such as a ground rod or metal water pipe, to the electrical system, providing a path for fault currents to flow back to the source. Proper sizing and installation of GEC are essential for effective grounding. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC must be large enough to safely carry the maximum fault current that could occur in the system. If the GEC is too small, it could overheat and melt, creating a fire hazard. The GEC must be made of copper or aluminum and must be protected from physical damage. It can be run exposed or concealed, but it must be securely fastened to the surface on which it is installed. The GEC must be connected to the grounding electrode using an approved method, such as a clamp or lug. The connection must be tight and corrosion resistant to ensure a reliable electrical connection. The GEC must be continuous and unbroken from the grounding electrode to the electrical system. Splices are not permitted in GEC as they can create a point of weakness in the grounding system. If the GEC must be run through a wall or floor, it must be protected by a conduit or sleeve. This will prevent the GEC from being damaged by abrasion or physical stress. The GEC must be identified with a green color or with green tape. This will help to ensure that it is not mistaken for a current carrying conductor. The NEC requires that the GEC be installed in a manner that is accessible for inspection and testing. This will allow electricians to verify that the GEC is properly sized and connected. In addition to the GEC, there is also a bonding jumper that connects the equipment grounding conductors to the grounding electrode system. The bonding jumper must be sized according to NEC Table 250.102. Seat 1 and must be installed in a manner that is similar to the GEC. The equipment grounding conductors provide a path for fault currents to flow from electrical equipment back to the source. They are typically run with the circuit conductors and are connected to the metal enclosures of electrical equipment. The grounding electrode system, including the GEC and bonding jumper, must be properly maintained to ensure its effectiveness. This includes periodically inspecting the connections for corrosion and tightness and testing the resistance to ground. The NEC provides detailed requirements for the installation and maintenance of grounding electrode systems. These requirements are designed to ensure that electrical systems are properly grounded and that people and equipment are protected from electrical shock and fire hazards. The IEEE standard, titled IEEE Guide for Safety in AC Substation Grounding, provides comprehensive guidelines for designing and installing grounding systems in AC substations. This standard is widely recognized and used by electrical engineers and designers to ensure the safety of personnel and equipment in substations. The IEEE standard covers a wide range of topics related to substation grounding, including the purpose of grounding, the types of grounding systems, the design of grounding grids, and the testing and maintenance of grounding systems. One of the key principles of the IEEE standard is to limit the step and touch potentials in a substation to safe levels. Step potential is the voltage difference between 2 points on the ground that are steps length apart. Touch potential is the voltage difference between a grounded object and a point on the ground that can be touched simultaneously. The IEEE standard provides equations and guidelines for calculating step and touch potentials and for designing grounding systems that will limit these potentials to safe levels. The design of the grounding grid is a critical aspect of substation grounding. The grounding grid is a network of interconnected conductors that are buried in the ground. The purpose of the grounding grid is to provide a low impedance path for fault currents to flow back to the source. The IEEE standard provides guidelines for determining the size, spacing, and depth of the conductors in the grounding grid. The IEEE standard also covers the bonding of equipment to the grounding grid. All metal equipment in the substation, such as transformers, circuit breakers, and switchgear, must be bonded to the grounding grid to ensure that they are at the same potential as the ground. This will prevent dangerous touch potentials from developing on the equipment. The testing and maintenance of grounding systems are also important aspects of the IEEE standard. Grounding systems should be tested periodically to ensure that they are functioning properly. The testing should include measurements of the grounding resistance and the step and touch potentials. The grounding system should also be inspected for corrosion and damage. The IEEE standard is a complex and comprehensive document, but it is essential for ensuring the safety of personnel and equipment in AC substations. Electrical engineers and designers should be familiar with the requirements of the IEEE standard and should use it as a guide when designing and installing substation grounding systems. The IEC 60079 series is a set of international standards that cover the requirements for electrical equipment used in explosive atmospheres. These standards are widely recognized and used by manufacturers and users of electrical equipment in industries such as oil and gas, chemical processing, and mining. The IEC 60079 series is divided into several parts, each of which covers a specific aspect of electrical equipment used in explosive atmospheres. Some of the key parts of the IEC 60079 series include IEC 60079-0, which covers general requirements for electrical equipment, IEC 60079-1, which covers flameproof enclosures, IEC 60079-7, which covers increased safety, IEC 60079-11, which covers intrinsic safety, and IEC 60079-13, which covers equipment protection by pressurized enclosure P. The IEC 60079 standards specify the requirements for the design, construction, testing, and marking of electrical equipment used in explosive atmospheres. The standards also specify the requirements for the installation, inspection, and maintenance of electrical equipment. One of the key concepts in the IEC 60079 standards is the concept of equipment protection levels, or EPLs. The EPL is a measure of the level of protection provided by the equipment against the risk of ignition. There are 3 EPL defined in the IEC 60079 standards GOT, which is for equipment that is intended for use in areas where an explosive atmosphere is present continuously or for long periods, GB, which is for equipment that is intended for use in areas where an explosive atmosphere is likely to occur occasionally, and GC, which is for equipment that is intended for use in areas where an explosive atmosphere is not likely to occur in normal operation but may occur infrequently. The IEC 60079 standards also specify the requirements for the selection of electrical equipment for use in different zones. Zones are classified based on the frequency and duration of the presence of an explosive atmosphere. There are 3 zones defined in the IEC 60079 standard. Zone 0, which is an area where an explosive atmosphere is present continuously or for long periods. Zone 1, which is an area where an explosive atmosphere is likely to occur occasionally. And Zone 2, which is an area where an explosive atmosphere is not likely to occur in normal operation but may occur infrequently. The IEC 60079 standards are complex and comprehensive, but they are essential for ensuring the safety of electrical equipment used in explosive atmospheres. Manufacturers and users of electrical equipment in these industries should be familiar with the requirements of the IEC 60079 standards and should use them as a guide when designing, installing, and maintaining electrical equipment.